Hi. So in this part of the lecture, we will look at what is called as the simplex method. We had solved our LP problems using the graphical technique in the previous lectures, and one of the limitations of graphical techniques is that if the number of variables goes beyond 2, solving that and interpreting the result becomes complicated. So the simplex method is one of the most widely used techniques and an algorithm that bypasses that limitation. Before we look into the details of the algorithm, let's set up some groundwork and we look at a few basics. Here we are going to define what we are going to call as our standard form. And why do we need a standard form? This is so that we can make an intuitive and understandable simplex method, and we can follow that algorithm consistently. So here is our LP standard form. I have quoted the word R because different authors may have different standard forms. The standard form that we will consider, we will always want our objective function to be of kind maximize. For example, an objective function for us would be represented as maximize z is equal to c1x1 plus c2x2 and cn xn. The constraints will be presented as equalities in our LP standard form and not by inequalities such as greater than equal to or less than equal to. So here is an example. In this case, we see that a11x1 plus a12x2 plus so on a1nxn is equal to b1. And here are some other examples. And finally, the variables are positive. So all x1, x2 through xn's are greater than equal to 0. Well, we have set up our standard form, but it is obvious that not every LP is in a standard form. So we have to find a way to convert a non-standard LP into a standard form of LP that we can use with our algorithm. So here are some of the issues that we will find within a non-standard LP. The problem could be minimized because we know that LP can be used for minimizing. We have to find a way, how will you convert a minimizing problem into a maximizing problem? The next one is the inequality constraints. In almost all the problems we have done, majority of the constraints are less than equal to or greater than equal to. So they are always an inequality. So we have to find a way to convert an inequality to an equality if we have to convert a non-standard LP to our standard LP. The variables may be negative, although we haven't seen that example as yet, but it is possible that for some problems or some situations a variable may be negative. So how will we handle a negative variable? And finally, another form of non-standard could be a variable could be unconstrained. That is, it could take a value on either side of the 0. So let's look at the first one. We have to convert a minimum to a maximum. The solution is simple. So all we do is we multiply the objective function by a value of -1. And then if the problem is requiring us to find the minimum value, if you multiply it by -1 and solve it for maximum value, you will still get the answer to the minimum value. Example, if we have a function, objective function, that requires us to minimize z is equal to 41x1 plus 30x2, it is mathematically equal to maximize z is equal to minus 41x1 minus 30x2. So we simply multiplied the right hand side with a -1, and by doing so we are able to use the logic or the algorithm for maximizing the objective function. So mathematically both of them are same. Now we have to convert a less than equal to an equal to. Here is a new term that we will use. It is called as a slack variable. So what we are going to do is, in order to remove the less than equal to sign, we will add a slack variable where slack variable's value is greater than equal to 0. So if we have an inequality given by 41x1 plus 30x2 is less than equal to 5, and we add a slack variable s1 which is greater than 0, you can easily interpret that the two equations are mathematically the same. One more note about slack variable is that it is a measure of an unused resource. If we apply a little bit of math on this side, on this equation, and move everything except the slack variable onto the right, our slack variable equals 5, in this case minus 41x1 plus 30x2 in a parentheses. The next one is the opposite of the previous case. Instead of less than equal to, how do you convert a greater than equal to the equal to? In this case, we subtract a new surplus variable. So, example is that we have 41x1 plus 30x2 is greater than equal to 5. The inequality is greater than equal to. Mathematically, this is equal to 41x1 plus 30x2 minus s2 is equal to 5, where s2 is greater than 0. So if you think about this, if s2 is greater than 0, that means that this side of the equation is greater than 5. So s2 is the surplus variable, and it is a measure of amount of excess that we have. Similarly, mathematically, s2 is equal to 41x1 plus 30x2 minus 5 in this case. Now, the third issue is eliminating a negative variable. What we do is we use a new variable which is the negative of the negative variable. This will get clear as we look into this example. So for example, we have x1 is less than 0. What we will do is we'll replace x1 with a new variable called y1 which is greater than equal to 0. So to get the optimum solution, minus y1 should be used. Eliminating the unconstrained variable, in this case we will use two variables instead of a single one, and both of them can take independent values, but individually they are greater than equal to 0. So example, if we have x1 ranging from minus infinity to plus infinity, and we replace that x1 by a difference of y1 minus y2, where y1 and y2 both are greater than equal to 0, but they can independently take any values. So in such a case, to get the optimal solution of the original problem, y1 minus y2 will be used. So for example, if y1 takes a value of 4 and y2 takes a value of 5, then y1 minus y2 is negative. Whereas if y1 takes a value of 5 and y2 takes a value of 4, then y1 minus y2 is positive. So that means this representation of y1 minus y2 is equivalent to x1.